birds go quiet, herds move restlessly, spooked by something they can't see. Something invisible has changed the world and nothing will be quite the same again. What you don't know, what you can't possibly know, is that 5,000 miles to the east, the Earth has just torn itself apart. On an island that will one day be called Sumatra, a supervolcano has detonated with a force almost beyond comprehension. The largest explosive eruption in 25 million years, enough material ejected into the atmosphere to bury all of South Asia under a blanket of ash. Enough sulfur launched into the stratosphere to dim the sun across half the planet. The blast left behind a crater so massive it now holds a lake 100 kilometers long. And according to some scientists, it nearly killed every last one of us. The claim sounds almost absurd. That humanity, our entire species, was reduced to maybe 2,000 survivors, that we came within a few thousand individuals of vanishing forever, that the eruption of a single mountain rewrote our DNA in ways we're still discovering today. But here's what makes this story so fascinating. The truth turns out to be even stranger and more layered than that headline suggests. Because when you start digging into what really happened 74,000 years ago, you find yourself on a journey through 3 different timescales: the hours and days of the eruption itself, ash and darkness spreading across a continent, the centuries and millennia of climate chaos that followed or maybe didn't, depending on which evidence you trust, and finally, the deep time written in our genes, bottlenecks and crashes and expansions stretching back not just 74,000 years, but nearly 1 million. If you're listening to this to fall asleep, that's exactly why I make these. So maybe subscribe and tell me, where are you right now and what time is it? I love checking the comments. It's like Berlin at breakfast and Boston at bedtime, all of us scattered across the world contemplating this one shared ancestral story. The Toba supervolcano is real. The eruption happened. The ash is still there, buried in layers across 2 continents. But did it really bring humanity to the brink of extinction? Did 2,000 survivors huddle in some unknown refuge while the rest of the world froze? Or is the story more complicated, more interesting, and ultimately more hopeful than we first thought? Let's go back, way back, to the day the sky went dark. Before we get to the eruption, before we watch the mountain explode and the ash fall, we need to understand what kind of world it was falling into. Because 74,000 years ago, Earth was already a challenging place to be human. This wasn't some Eden interrupted by catastrophe. This was a planet deep in the grip of an ice age, where survival was never guaranteed and small populations were always just one bad season away from disaster. The technical term is marine isotope stage 4. The transition from MIS5A into 4 had just occurred, meaning the planet was sliding into a colder phase. Ice sheets that had retreated during warmer periods were advancing again across the northern hemisphere. In North America, glaciers were spreading south from Canada. In Europe, ice was creeping down from Scandinavia. These weren't just snowfields. These were walls of ice sometimes 2 miles thick, grinding continents beneath their weight, locking up so much water that global sea levels had dropped somewhere around 80 meters below where they are today. Think about what that means. Coastlines you know from maps didn't exist. Where there's now open ocean between mainland Asia and Indonesia, there was land. The Sunda Shelf was exposed, connecting what we now call Thailand, Malaysia, Sumatra, Java and Borneo into a single enormous peninsula. Australia and New Guinea were joined as Sahul. Britain was still attached to Europe. The world's geography was fundamentally different. You could walk to places that now require boats. This exposed continental shelf wasn't wasteland either. These were productive environments, river valleys and coastal plains and forests that supported substantial populations of animals, and probably humans too. Populations that now drowned, their archaeological sites buried under 100 meters of seawater. When we talk about how many humans existed 74,000 years ago, we're reading a record with whole chapters missing. Entire regions where people might have lived are now underwater, inaccessible, invisible to us. So who were these humans? If you could somehow take a census of Earth in 74,000 BC, what would you find? Homo sapiens had been around for something like 200,000 years by this point, maybe longer depending on how you define the species. Early modern humans with anatomy basically indistinguishable from ours. But we were still a relatively modest, geographically limited group. Most of the human population was in Africa, scattered across the savannas and woodlands and forest edges, wherever resources could support small bands. There had been earlier attempts to expand beyond Africa. During wetter periods in the preceding tens of thousands of years, Homo sapiens groups had pushed into the Levant, into Arabia during green phases when monsoons turned deserts into grasslands. But many of these early expansions seem to have failed, populations contracting back or disappearing entirely when climates shifted. By 74,000 years ago, we probably weren't very numerous outside Africa. Maybe some small pioneering groups clinging to southern Asian coastlines, maybe populations scattered across the Middle East, but nothing like the global dominance that was still millennia in the future. And we weren't alone. This is crucial to understand. The planet in 74,000 BC was home to multiple human species, all competing for resources, all adapted to different environments. In Europe and Western Asia, you had Neanderthals, robust and cold-adapted, master hunters of Ice Age megafauna. In Eastern Asia, there were Denisovans, known mostly from genetic traces but clearly successful across enormous territories. On the Indonesian island of Flores, there was Homo floresiensis, the so-called hobbit people, a diminutive species that had survived in isolation for tens of thousands of years. Our species was just one player among several, not yet dominant, not yet inevitable. The climate itself was volatile in ways that are hard to appreciate from our relatively stable modern perspective. This wasn't just a steady cold period. The late Pleistocene was characterized by what scientists call Dansgaard-Oeschger events, abrupt climate oscillations that could swing temperatures in the northern hemisphere by several degrees in just decades. These weren't gradual changes. These were whiplash shifts driven by changes in ocean circulation and ice sheet dynamics. Monsoons would strengthen and weaken. Rainfall patterns would shift. Entire ecosystems would transform within a human lifetime. The world was already testing us, already pushing human populations to adapt, migrate, or die. The stage was set for catastrophe. And then the mountain exploded. The mountain that was about to reshape human history didn't appear overnight. Toba was the product of a geological process that had been building for millions of years, a consequence of Earth's restless crust grinding against itself in slow motion. Picture the floor of the Indian Ocean, hundreds of kilometers south of Sumatra. The Indo-Australian tectonic plate is moving northeast at roughly 6 or 7 centimeters per year. Not fast by human standards, but relentless. And it's not sliding past the edge of Southeast Asia. It's diving underneath it, plunging down beneath the sunder plate in what geologists call a subduction zone. One piece of Earth's crust literally sinking beneath another, descending into the hot mantle below. As that oceanic crust descends, something crucial happens. It's not just rock down there. It's rock that's been sitting on the ocean floor for millions of years, saturated with seawater, carrying hydrated minerals down into the depths. And when that water-rich rock gets dragged down to depths of 100–150 kilometers, where temperatures reach 1,000 degrees Celsius, the water does something remarkable. It lowers the melting point of the surrounding mantle rock. Suddenly, rock that should still be solid begins to melt. Magma forms. And because it's less dense than the solid rock around it, it starts rising. Slowly at first, percolating upward through fractures and weak zones in the crust. As it rises, it accumulates, pools, forming vast chambers of molten rock kilometers beneath the surface. This is how the Sunda volcanic arc formed, the chain of volcanoes stretching along Sumatra and Java, and Toba sits right in the middle of it. But Toba wasn't just another volcano. The magma-feeding Toba was special, or perhaps we should say, dangerous. As magma rises and sits in crustal chambers, it evolves. The first minerals to crystallize out tend to be dense, iron-rich compounds that sink. What remains becomes increasingly enriched in silicon, aluminum, and dissolved gases. The magma becomes rhyolitic, thick and viscous like cold honey. And crucially, it becomes loaded with water vapor and carbon dioxide, gases dissolved under immense pressure. This is the recipe for catastrophic eruptions. Basaltic magma, the kind that feeds Hawaiian volcanoes, is fluid. It flows relatively easily, releasing gases gradually. When it erupts, you get lava fountains and flows, dramatic but manageable. Rhyolitic magma is different. It's so viscous that gases can't escape easily. Pressure builds and builds, until eventually the rock can't contain it anymore. Beneath Toba, geophysical imaging suggests there wasn't just one magma chamber. There was a complex system, a stack of what scientists call magma sills or lenses, Pancake-shaped bodies of molten rock spread across an area 10 or 20 kilometers wide, sitting at various depths between 7 and 30 kilometers beneath what is now Samosir Island in the middle of Lake Toba. At the top of this system, in a relatively shallow chamber just a few kilometers down, the most evolved, gas-rich, explosive magma was accumulating, and it had time, hundreds of thousands of years. Because Toba had done this before, the geological record shows at least 4 major caldera-forming eruptions at Toba. The first, the Harangal Dasiti eruption, happened roughly 1.2 million years ago. Then came the oldest Toba tuff around 840,000 years ago. The middle Toba tuff followed about 500,000 years ago. Each time, enormous volumes of magma erupted explosively. Each time, the overlying crust collapsed into the emptied chamber, forming a caldera, a volcanic depression miles across. Each time, the landscape of northern Sumatra was reshaped, buried under thick blankets of volcanic deposits. These weren't small events. The oldest Toba eruption alone probably ejected something like 2,000 to 2,500 cubic kilometers of material. That's already larger than any eruption in recorded human history. But they were just rehearsals. By 74,000 years ago, the magma system beneath Toba had been recharging for 500,000 years since the last major eruption. Fresh magma rising from below, existing chambers crystallizing, differentiating, becoming more evolved. The shallow reservoir accumulating a catastrophic volume of rhyolitic melt, superheated, gas-saturated, building pressure against the relatively thin roof of overlying rock. The numbers, when you finally see them laid out, are almost incomprehensible. The youngest Toba eruption ejected somewhere between 2,800 and 3,200 cubic kilometers of dense rock-equivalent material. Dense rock equivalent is important because it accounts for the fact that pumice is full of bubbles. When scientists talk about eruption volumes, they're estimating what the volume would be if you compressed all that frothy pumice back down into solid rock. The actual volume of material as it came out was even larger. Let's try to make that scale tangible. Mount St. Helens in 1980 ejected about 1 cubic kilometer. The eruption that decapitated the mountain, that sent ash across multiple states, that became one of the most iconic volcanic events in American history, was 1 cubic kilometer. Krakatoa in 1883, the eruption that killed tens of thousands and was heard thousands of miles away, ejected roughly 25 cubic kilometers. Tambora in 1815, which caused the year without a summer and probably killed more people than any other volcanic eruption in recorded history, released about 160 cubic kilometers. Toba was 2,800 to 3,200, 20 times Tambora, more than 100 times Krakatoa. If you could somehow take all the material Toba ejected and spread it evenly across the entire United Kingdom, you'd bury the country under roughly 13 meters of rock, over 40 feet of volcanic deposits covering an area the size of a small nation. And the eruption mechanism itself was the stuff of planetary nightmares. When the pressure finally exceeded the strength of the overlying rock, the mountain didn't just erupt, it exploded. The eruption column punched through the troposphere, through the stratosphere, reaching heights probably exceeding 40 kilometers, higher than most commercial jets fly, high enough that ejected material entered the stratospheric winds that circle the planet. As enormous volumes of magma emptied from the chamber, the roof collapsed, not gradually, catastrophically. Thousands of cubic kilometers of rock dropping hundreds of meters, maybe kilometers, into the void. The surface above didn't just sink, it fragmented, shattered, creating a caldera roughly 100 kilometers long and 30 kilometers wide, one of the largest volcanic depressions on Earth. The column collapse generated pyroclastic flows, avalanches of superheated gas and pulverized rock, moving at speeds that might have exceeded 300 kilometers per hour. These weren't just hot. They were hundreds of degrees Celsius, incinerating everything in their path, flowing across the landscape like liquid, but faster and far more destructive. Near the vent, these flows deposited ignimbrate sheets, welded volcanic rock hundreds of meters thick in places, and the ash went everywhere. Carried by high-altitude winds, Toba ash has been found in sediment cores from the South China Sea, from the Indian Ocean, from ice cores in Greenland. A geological signature of a single catastrophic day that would be readable in Earth's rock record for millions of years. The volcano was ready, the planet was vulnerable, and the clock was running out. Nobody alive 74,000 years ago could have known what was coming. No written records, no seismographs, no emergency broadcasts, just the Earth itself, beginning to send signals that something fundamental was about to break. The first warnings probably came weeks, maybe months before earthquakes. Not the catastrophic shaking that would come later, but persistent tremors, the kind that make water ripple in containers, that wake people at night. Magma pushing upward, fracturing rock, forcing its way toward the surface. Animals might have sensed it first, behaving strangely, migrating away from areas they'd inhabited for generations. Hot springs getting hotter, fumaroles opening in the ground, venting sulfurous steam. Then, maybe days before the main event, the earthquakes intensified. Ground that had been solid for thousands of years began heaving, cracking, trees toppling, rock slides cascading down slopes. Anyone living within sight of the mountain would have known something was terribly wrong, but there was nowhere to go, no frame of reference for what was building beneath their feet. When it finally began, probably sometime in the hours just before dawn, the initial blasts were phreatic. Groundwater, superheated by rising magma, flashing instantly to steam. The pressure building until rock shattered, sending columns of steam and pulverized stone thousands of meters into the air. These weren't the main event. They were the mountain's way of clearing its throat. Within hours, maybe minutes after those first blasts, the magma reached the surface, and the character of the eruption changed completely. Now it wasn't just steam, it was molten rock, gas-charged, exploding upward with a violence that probably registered on seismographs that wouldn't be invented for another 73,000 years. The Plinian column, a roaring pillar of ash and gas and pulverized pumice, climbing at speeds that might have approached the speed of sound in the lower atmosphere. 30 kilometers up, 35, 40 kilometers, punching through the stratosphere. At that altitude, there's almost no weather. The ash wasn't being carried by local winds anymore. It was entering the planetary circulation system, the jet streams that would distribute it across continents. Below the rising column, the scenario was already apocalyptic. The eruption was so violent, ejecting material at such rates that the volcanic edifice couldn't structurally support what was happening. The ground began collapsing, not gradually, in catastrophic pulses, thousands of cubic kilometers of overlying rock dropping into the emptying magma chamber, fragmenting, mixing with erupting magma, generating pyroclastic density currents that defied imagination. These flows weren't lava. They were avalanches of superheated gas and rock fragments, moving like fluid but deadly in ways that fluid isn't. Temperatures inside the flows probably exceeded 400, maybe 500 degrees Celsius, hot enough to carbonize wood instantly, hot enough to melt glass, and they moved fast. Computer models suggest velocities of 200 to 300 kilometers per hour, maybe faster in the initial surges. Everything in their path simply ceased to exist. Forests incinerated in seconds, rivers boiled away, the flows coursed down valleys, across lowlands, extending tens, possibly hundreds of kilometers from the eruption center. Some probably reached the Indian Ocean to the west, the Strait of Malacca to the east. Eyewitnesses, if any survived at sufficient distance, would have seen glowing avalanches of destruction expanding outward like the shockwave from an explosion, which, in a sense, is exactly what they were. The ignimbrite sheets they deposited are still there today, buried beneath vegetation and soil. Near the caldera, deposits hundreds of meters thick, further out tens of meters, layers of welded volcanic glass and pumice that cooled so slowly they partially crystallized, creating what geologists call tuff, compressed volcanic rock that in places forms cliffs and mountainsides across northern Sumatra. But the truly planetary-scale destruction was just beginning. The ash column, now 40 kilometers high, was spreading laterally. At those altitudes, it encountered stratospheric winds capable of carrying particles around the world. Within days, maybe a week, Toba ash was falling across South Asia, across the Indian subcontinent, across islands in the Indian Ocean. Fine grey powder drifting down from darkened skies like snow, except it didn't melt. It accumulated. Sites in India have been found with youngest tuba tuff layers 10 to 15 centimeters thick. That's 6 inches of volcanic ash, thousands of kilometers from the eruption. In Malaysia and parts of Indonesia closer to the source, deposits measured in meters. The ash blanketed an estimated 7 million square kilometers of land and ocean. Roughly 7 or 8% of Earth's entire surface covered in a geological instant. Imagine you're part of a small band of early humans somewhere on the Indian subcontinent. Homo sapiens, or perhaps late archaic humans, living in a world already marginal, already cold because you're in the grip of a glacial period. You've never heard of volcanoes. You have no concept that the Earth itself can explode. One morning, the sun doesn't rise properly. There's light, but it's wrong. Dim. The sky has a grey cast that doesn't clear. By midday, you realise the sun itself looks pale, distant, like you're seeing it through smoke, but there's no fire. Then the ash starts falling. At first just a dusting, easy to brush off, but it keeps coming, day after day, coating leaves, choking water sources, getting into food, making people cough. Plants that were green start turning brown. Animals grow thin, confused, their food sources disappearing beneath the grey blanket. You have no framework for understanding that an explosion happened on an island thousands of kilometers away. No way to know that what you're experiencing is ash fallout from the largest volcanic eruption your species would ever witness. All you know is that the world is ending, and you don't know why. But even the ash wasn't the worst part. The eruption had injected enormous quantities of sulfur dioxide into the stratosphere. Estimates vary, but we're talking about hundreds of millions of tons, possibly billions. At stratospheric altitudes, sulfur dioxide reacts with water vapor to form sulfuric acid aerosols, tiny droplets that remain suspended for years, forming a global veil that reflects incoming sunlight back into space. This is the mechanism of volcanic winter, not the ash, which settles relatively quickly, the aerosols. For months, maybe years after the eruption, the planet's surface received measurably less sunlight. Temperatures dropped. How much is still debated. The cooling might have been several degrees in some regions, less in others, but even a few degrees sustained over years would be catastrophic for ecosystems already stressed by ice age conditions. And 9 to 14 days after it began, the main eruptive phase finally exhausted itself. The magma chamber, drained of its most volatile gas-rich melt, could no longer sustain the column. The eruption sputtered, diminished, stopped. What remained was a hole in the earth, a caldera 100 kilometers long and 30 kilometers wide, a wound in the planet's crust that would eventually fill with water, creating Lake Toba, today one of the largest and most beautiful volcanic lakes on Earth. Serene, peaceful, surrounded by lush tropical forests, a popular tourist destination where people swim and fish and take photographs of stunning sunsets over calm water. You would never know, looking at it today, that this tranquil lake sits inside the scar of an explosion that changed the course of human history. That beneath that placid surface lies a volcanic system that could, given enough time, do it all again. But 74,000 years ago, in the immediate aftermath, there was no lake yet, just a smoking crater and a world going dark. In 1998, an anthropologist named Stanley Ambrose sat with the pieces of a puzzle spread out before him. On one side, geology, evidence that 74,000 years ago, Toba didn't just erupt, it detonated with a force almost beyond measurement. On the other side, genetics, the strange fact that modern humans, for all our numbers and variety, are surprisingly alike under the skin, less genetically diverse in many measures than chimpanzees or gorillas or orangutans with far smaller ranges. Ambrose's idea was simple and terrifying. What if those two facts were connected? What if, when Toba blew, it almost erased us? The mechanism he proposed felt elegant, almost inevitable. Toba injects vast amounts of sulfur dioxide high into the stratosphere. There, where weather barely reaches, the gas reacts with water vapor, forming an invisible veil of sulfuric acid droplets. Not big raindrops, but particles so fine they can hang in the upper atmosphere for years. Those particles do one main thing very well. They bounce sunlight back into space. If you've heard of the year without a summer after Tambora erupted in 1815, you've seen a small version of this. Crops failed across Europe. Frosts came in June. Skies turned a milky, unsettling white. But Tambora was tiny compared to Toba. Ambrose argued that if a VAI-8 super eruption like Toba could loft enough sulfur that high, the result wouldn't just be a bad year. It could be 6 to 10 years of cold, dimmed light, a volcanic winter. Early climate models backed up the possibility. Some simulations suggested global temperatures might fall 3 to 5 degrees Celsius. A world already in an ice age, shoved a step deeper into the cold. In some regions, especially continental interiors or high latitudes, the modelled cooling was even harsher. 10, maybe 15 degrees colder, at least for a while. The kind of drop that doesn't just chill evenings, It restructures ecosystems. Less sunlight means less photosynthesis. Trees grow slowly, or not at all. Grasses fail to sprout on schedule. In the oceans, tiny photosynthetic plankton struggle, dimming the base of the marine food web. The effect doesn't have to be absolute to be devastating. A 20% drop in plant productivity, sustained over years, can echo upward through every level of life. Herbivores find less to eat. Their numbers fall. Predators that depend on them grow thin, desperate, then disappear. For human hunter-gatherers, exquisitely tuned to the seasonal movements of animals and plants, the world itself seems to stop keeping its promises. Migrations fail. Rivers freeze earlier. Fruits don't ripen when they should. The familiar calendar of survival breaks. In the Toba catastrophe picture, that's exactly what happened. Ash and aerosols dim the sun, temperatures fall, rainfall patterns shift. Across Africa and Asia, already cool, dry landscapes tip into something harsher. Not everywhere, not equally, but in enough places that human populations, already small, begin to fracture. Some bands perish outright, caught in regions where plant and animal life simply can't keep up with the combined stress of ice age and volcanic winter. Others retreat into refugia, small pockets where local conditions remain just tolerable enough. Maybe along coasts where the ocean moderates the climate. Maybe in deep river valleys or near persistent springs and wetlands, places where a little greenery clings to life. In this view, Homo sapiens doesn't glide smoothly through the late Pleistocene. It stumbles, it crashes. A global population of perhaps hundreds of thousands, still modest by modern standards, shrinks rapidly to only a few thousand souls. Ambrose spoke cautiously of a few thousand survivors. Popular science took that phrase and gave it an edge. 10,000, 3,000, 2,000, 1,000 breeding pairs. Different retellings chose different numbers, but the message was the same. We almost didn't make it. To understand what that would mean for our DNA, imagine a glass jar filled with marbles. Tens of thousands of them, in hundreds of subtly different colors. Each color is a genetic variant, a slightly different version of a gene, or a small stretch of DNA. This is your species before the catastrophe. Rich, varied, every color a possibility. Now tilt the jar and let almost all the marbles fall away. Earthquakes of hunger and cold shaking the jar decade after decade. At the end, you scoop up a small handful that happened, by sheer luck, to remain. Maybe it's 3,000 marbles, maybe 10,000, maybe only 2,000. However many it is, your handful doesn't carry all the colors from the original jar. Some shades are gone forever. Others are suddenly common, not because they were better, but because they were in the right place at the right time. Every marble you add in the future, every descendant born from that moment on, must be drawn from the colors in that reduced handful. This is a genetic bottleneck, a narrowing of the passage through which all future diversity must flow. When geneticists first began to read human DNA at scale, they saw something that looked very much like the aftermath of such a narrow passage. Compared to chimpanzees, whose populations have been divided and reunited many times across Central Africa, humans looked strangely uniform. Most of our genetic variation was shallow. Different, yes, but not deeply diverged. Analyses using tools like coalescent theory suggested that, at some point in the late Pleistocene, the effective size of our breeding population had dipped to only a few thousand individuals. Ambrose's hypothesis fit perfectly into that gap. Here was a documented planetary scale event, precisely dated to around 74,000 years ago. Here was a genetic signal hinting at small ancestral populations somewhere in the same broad window of time. It was irresistibly tempting to draw a straight line between them. Toba explodes, the sky darkens, temperatures fall, ecosystems reel, humans nearly vanish. Our genetic diversity plummets, squeezed through a bottleneck of a few thousand survivors in scattered refuges. And from that remnant, every person alive today descends. It's easy to see why this narrative caught fire. It had everything. A single, spectacular geological event, a global climate disaster, a razor's edge escape from extinction. And perhaps most appealing of all, it offered a clean, cinematic explanation for a messy scientific observation. Why you and a stranger on the far side of the world are, at the molecular level, such close cousins. The story spread quickly. It appeared in books and magazine articles, in television specials about supervolcanoes, in lectures where professors would tell students that at one point, maybe only 2,000 of our ancestors huddled under darkened skies, the fate of the species resting on their fragile shoulders. The numbers varied from telling to telling, but the image stayed fixed. A tiny band of humans standing at the edge of an abyss carved by a Sumatran volcano. And like many compelling stories, it lingered. It wove itself into the way people thought about human uniqueness, about our shared vulnerability, about the stroke of luck or misfortune that could have erased us before history even began. But science is a restless thing. As new data accumulated from lake sediments in Africa, from ice cores, from more detailed genetic studies, the neatness of the Toba catastrophe picture began to fray. The classic theory, with its brutal volcanic winter and its handful of survivors, would not go unchallenged. To see why, we have to look again at the evidence, at what the rocks, the climate, and our own DNA really say about 74,000 years ago. If you want to test a story about global catastrophe, you don't start with myths or memories. You start with mud. Picture a long, slender cylinder of lake sediment, lifted slowly from the bottom of an East African lake, layer upon layer, year upon year, like pages in a book that has been quietly writing itself for tens of thousands of years. Dust from distant deserts, pollen from trees on the shore, tiny fragments of charcoal from ancient fires, silica bodies from grasses and reeds, phytoliths, each one a microscopic fingerprint of the plant it came from. Somewhere in that stack of layers there should be a moment when the sky went dark. At Lake Malawi, a deep rift lake in East Africa, scientists have that book in their hands. When they scan down through the layers, they find what they were looking for: a thin but unmistakable band of volcanic ash. Chemically, it matches Toba, the fallout of that Sumatran super eruption, carried halfway across the world and gently settling onto the water surface. On the catastrophe picture, everything below that ash is the before world, everything above it is after. If Ambrose's volcanic winter happened as imagined, years of dimmed sunlight, collapsed ecosystems, mass die-offs, then this is where the story should twist. Below the ash, one pattern. Above it, something utterly different. But that's not what the mud says. The phytoliths continue, almost as if nothing has happened. Grasses, woodland plants, the mix of vegetation around Lake Malawi shifts. Yes, but not abruptly. No sudden wholesale replacement of forest with barren ground. No decade-long absence of plant productivity. The charcoal fragments, the tiny signatures of ancient fires, tell a similar story. The fire regime before and after the ash looks continuous. People, lightning and dry seasons were still lighting landscapes on fire at much the same pace. There is a line of ash in the core, a silent record of an eruption that shook half the planet. But the lake's ecology doesn't seem to crash. In this part of Africa at least, there is no sign of a prolonged brutal volcanic winter, and this matters because East Africa is not just any backdrop. It is one of the main homelands of early Homo sapiens. If Toba had plunged our species to the brink, you might expect to see its fingerprints here: shrinking woodlands, altered grasslands, a break in the familiar dance of plants and fire. Instead, the record looks strangely calm. Shift your attention thousands of kilometers away to the Indian subcontinent. Here, the Toba ash isn't just a whisper in lake mud. In places, it lies on the ground in thick blankets, meters deep in ancient landscapes. If humans lived here before the eruption and died out in its wake, their traces should be interrupted. Tools below, emptiness above, or a different culture stepping into the gap. At sites like Jwalapuram, in what is now the Kurnool district of India, archaeologists have been patiently peeling back those layers. They find stone tools, flaked points, scrapers, cores, embedded in sediments that were once open ground. Above those sediments, the Toba ash, a distinct, pale band. Above the ash, more tools. When researchers compare the technology below and above that dividing line, a pattern emerges. It looks familiar. The way flakes are struck from cores, the shapes of points and scrapers. The overall signature of the toolkit remains remarkably similar across the ash. There is no dramatic collapse into cruder technology, no long hiatus where people vanish, then later reappear with a wholly different way of making tools. It looks, instead, like continuity. Like some group of hominins, perhaps early Homo sapiens, perhaps closely related cousins, were living there before Toba, saw the ash fall, endured whatever followed, and kept on napping stone much as they had before. That doesn't mean the eruption was a non-event in India. Local environments could still have been harshly disrupted. Ashfall can choke rivers, smother plants, force people to move. Populations might have dropped or shifted without leaving a clean break in the stone record. But the image of India emptied of humans, then slowly repopulated from some distant refuge, no longer fits well with what the ground is showing us. While archaeologists and geologists were reading these quiet lines of continuity, climate scientists were revisiting the other half of the picture, the sky. Early models of Toba's impact treated it as a scaled-up version of known eruptions, injecting enormous amounts of sulfur high into the stratosphere and keeping it there. The result on the computer screen was a planet plunged into years of deep cold. But as models improved, higher resolution, better physics for aerosols, more realistic data from recent eruptions like Pinatubo and Tambora, the numbers began to shift. Sulfur yield, particle size, how droplets clump together and settle out. These details turned out to matter immensely. Tiny changes in assumptions produced big differences in the modelled climate response. Some newer simulations still show significant cooling, global average temperatures dropping a degree or two. In the coldest regions, especially in the northern hemisphere, more than that. But the duration looks shorter, often a few years of strong anomalies, not a frozen decade that remakes every ecosystem on Earth. Most models now show a world that is knocked hard, but then recovers toward its previous state on human, rather than geological timescales. And importantly, the cooling is not uniform. High latitudes in the north, already sitting under Ice Age conditions, take a heavy hit. Some simulations show parts of Asia and Europe becoming even more hostile, with longer winters and altered rainfall. But closer to the equator, especially in the tropics of the southern hemisphere, the signal is often muted. In some Antarctic records, the response to Toba is surprisingly subtle, or even ambiguous. When you overlay that patchwork of modelled climate impacts with what we know about where humans were, a picture starts to form. At 74,000 years ago, our species was still primarily African, with small or transient populations reaching into Western and Southern Asia. If East Africa and other tropical refuges were partially buffered, still dimmer, still cooler, but not catastrophically so, then the heartlands of Homo sapiens may have escaped the worst of the volcanic winter. None of this exonerates Toba. The eruption was enormous. The ash reached across continents. The sulfur aerosols did change the climate, at least for a while. The immediate region around Sumatra would have been devastated. Local populations, human and non-human, would have faced horrors that don't easily fit into numbers or models. What is changing is not our sense that something big happened, but our confidence about what that something meant for our species as a whole. The strongest version of the catastrophe theory, the one where Toba single-handedly drives humans down to a mere 2,000 or 3,000 survivors, now looks, in the light of lake cores, stone tools, and refined climate models, more like a compelling story than a firmly established fact. When geneticists look at our DNA today, they do see signs that, in the past, our population was small. They see bottlenecks, dips, constrictions in the flow of genetic variation, but those signals are smeared out over time. They don't come stamped with labels saying caused by Toba or caused by Ice Age drought. When you line up the finest-grained genetic reconstructions with the precise timing of the Toba eruption, the match isn't as tight as people once assumed. The few thousand effective breeders that models infer for some periods of our history might not correspond to a sudden crash at 74,000 years ago at all. They might reflect a long period of being rare and scattered, or multiple smaller bottlenecks in different regions at different times, or earlier crises that predate Toba by hundreds of thousands of years. In other words, the jar of marbles was never as full as we imagined, and the hand that shook it may not have belonged to a single volcano. The more closely scientists read the evidence, the more the simple Toba story begins to blur. The eruption was real. The ash fell, temperatures dipped. Some places must have suffered terribly. But the idea that the entire human species was pushed through a razor-thin bottleneck by that one event alone, that we all descend from a tiny band of Toba winter survivors, is no longer the only or even the most likely explanation, which leaves a deeper mystery. If Toba did not almost erase us, why are we so genetically uniform? Where did the signal of near extinction come from? To answer that, we have to look past the dramatic, well-dated scar of a single super eruption and down into older, darker layers of our past, into a time when our ancestors weren't yet fully human as we know it, and when the world itself was in the grip of a far more protracted crisis. To understand that older, darker history, you have to do something strange. You have to take living people, right now, breathing and blinking under electric lights, and treat them as fossils, not fossils in stone, fossils in code. Imagine you could line up every copy of a particular gene from people all over the world. Every version of that stretch of DNA, from your cells, from mine, from a herder in East Africa and a fisher in the Philippines, from someone in Iceland and someone in the Amazon. Some of those gene copies would look almost identical. Others would differ at a few letters. A handful would be quite distinct, shaped by long histories in different corners of the planet. Now, instead of reading the code from left to right, imagine reading it backward in time. Every difference between two copies of a gene is like a tiny tick mark, created by a mutation in some ancestor long ago. The more differences there are, the further back you have to go to find the moment when those two copies were still one and the same, sitting in the chromosomes of a single person. Geneticists call that moment the coalescent, the point where two lineages merge into a common ancestor. If you trace all the versions of a gene in the world today back through their little trees of ancestry, something interesting happens. Branches keep fusing as you go deeper in time. 10 copies become 5 lines, 5 become 3, 3 become 1. Do that not just for the one gene, but for thousands scattered across the genome, and a pattern starts to emerge. When populations are large, with many people passing on their genes, these trees stay bushy. Lineages take a long time to merge. There are many different branches coexisting side by side, and you have to go far back before they meet. When populations are small, with fewer individuals breeding, the trees close in on themselves. Lineages coalesce quickly. They bump into the same ancestors over and over, because there just weren't many people alive to choose from. This is the essence of coalescent theory. You look at the way genealogical branches fold together as you walk back in time, and from that folding pattern, you infer how wide or narrow the river of ancestors must have been. If the branches stay wide and separate for a long stretch of time, that suggests a big population. If they collapse into a few common ancestors very suddenly, that suggests a bottleneck. It sounds abstract, almost like a math puzzle, but this is what modern population genetics rests on. Every mutation, every shared stretch of DNA you carry is a tiny timestamp. Add enough timestamps together, and you can sketch the rise and fall of populations that lived hundreds of thousands of years before anyone learned to write. But there's a wrinkle. When geneticists talk about the size of past populations, they don't usually mean how many humans were alive on Earth that day. They talk about something slipperier: effective population size. Effective population size, usually written as NE, is the size of an imaginary, perfectly well-mixed, perfectly random mating population that would give you the same pattern of genetic drift you see in the real world. In that perfect imaginary population, every individual has the same chance to reproduce. Sex ratios are even. There's no long-term structure, no isolated valleys or favored lineages. Real populations are nothing like that. Some people have many children, others have none. In some times and places, far more women than men leave descendants, or the other way around. Groups split and merge, migrate and isolate. Wars, famines, cultural rules about marriage and kinship. All of these skew who passes on genes and who does not. All of those skews shrink NE. The result is that effective population size is usually smaller, sometimes much smaller, than the actual head count. For many species, NE can be a 10th, a 20th, even less of the census size. A wild population of 50,000 animals might behave genetically like an idealized population of just 5,000. A human population spread across a continent might number in the hundreds of thousands, yet have an effective size of only tens of thousands. So when you hear a number like 2,000 survivors, or 1,280 breeding individuals, what the genetics is really whispering is subtler. At this point in time, the ancestors of living humans, taken together, behaved, genetically, as if there were only about this many idealized breeders. The real number of living bodies could have been significantly higher, perhaps several times higher, and even that 2,000 comes with fuzziness. Assumptions about mutation rates, generation lengths, how structured those ancient populations were, change the assumptions, and the number bends. Still, even with those caveats, the story in our DNA is striking. In 2011, two researchers, Hengley and Richard Durbin, took the coalescent idea and pushed it in a new direction. Instead of just looking at differences among many people, they asked, how much history can you recover from a single whole genome? Their method, with the calm technical name PSMC, pairwise sequentially Markovian coalescent, slides along one person's DNA, region by region, reading how often the two copies of each segment, the one from the mother and the one from the father, seem to share recent or ancient common ancestors. From the density of mutations and the way these ancestries cluster, the method reconstructs a rough timeline of effective population sizes, like a cardiogram of a species' heartbeat. When Lee and Durbin ran this on human genomes, they did not see a simple flat line with one enormous dip at exactly 74,000 years ago. They saw something more complicated. Long stretches where Ni hovered in the tens of thousands, gradual rises and falls, evidence of contractions and expansions, but not a single sharp worldwide plunge that neatly lined up with Toba's eruption. Different human genomes told slightly different stories. African lineages especially preserved deeper, more complex patterns, consistent with multiple subpopulations within Africa, splitting and mixing over long periods. Non-African genomes showed a clearer, more recent constriction, one that matched something else we know from archaeology and fossils. Around 60,000 to 70,000 years ago, a branch of our species left Africa for good. That movement, small in numbers at first, enormous in consequence, left a crisp signature in our DNA. Most people living today outside Africa trace a large fraction of their ancestry back to a relatively small group of migrants from a larger African population. That is a bottleneck. Not necessarily a brush with extinction, but a founder event, a few lineages stepping into a vast new world of empty territory. As those migrants spread through Arabia, into Eurasia, down the coasts of South Asia, into Australia and beyond, their descendants carried only a subset of the genetic variation that existed back home. Outside Africa, genetic diversity is lower, and the telltale patterns of coalescence lineages collapsing back into a small number of ancestors are stronger. This out-of-Africa bottleneck is one of the most robust findings in human genetics. It fits with fossils, with stone tools, with dates from multiple lines of evidence. But it is not the same thing as the Toba catastrophe. It does not require that the entire human species was reduced to a few thousand people, huddled in a single refuge by volcanic winter. It only requires that a subset of that species, a small river branching off the main channel, carried our lineage into the rest of the world. So why then do we, as a species, have such low genetic diversity compared to our close cousins, the other great apes? Chimpanzees and bonobos, even some gorilla populations, show more genetic variation across their range than all humans on Earth put together. It's as if they carry thicker bundles of ancestral threads, more tangled and diverse, while ours are a thinner, more uniform skein. Part of the answer seems to be that our effective population size has been modest for a long time. Even before the out-of-Africa journey, our ancestors may have lived in relatively small, scattered groups, rarely reaching the global numbers you might imagine. Part of it lies in structure. For much of our history, Africa itself seems to have hosted multiple semi-separate populations of early Homo sapiens and closely related forms. These groups would sometimes mix and sometimes drift apart, their genes weaving in and out like channels of a braided river. From the perspective of any one channel, the total flow looks smaller than the whole, and part of it is that our past is not a single bottleneck, but several. Local crises, climate swings, founder events when small bands pushed into new territories, each one shaving away a little variation here, a little there. On top of all this, natural selection itself can erode diversity in certain regions of the genome, especially where beneficial mutations have swept through populations or where harmful ones are pruned away over and over. That pruning can make our genetic forest look sparser than it truly was in terms of simple head counts. If you picture human history as a river, it's tempting to look for one giant concrete dam, a single disaster like Toba, squeezing the flow down to a trickle. But when geneticists read our DNA, they see something different. They see a river that narrows and widens many times. Long, shallow constrictions where numbers were low but not vanishing. Sudden, tight narrows where only a few lineages squeezed through. A migration here, a regional drought there. Side channels splitting off and carrying people into new lands, some drying up, others rejoining the main flow. What reaches the present is not a clean, straight line, but the combined result of every bend and every bottleneck. Every time our ancestors were few, and every time they were many. Toba may have been one rock in that river, one obstacle that deflected and disturbed the flow, but the low diversity we see today, the whispers of near misses with extinction, seem to come from something older, deeper, more prolonged than one eruption 74,000 years ago. To find that story, you have to follow the river much further upstream, into a time before Homo sapiens, when our ancestors were fewer than we ever imagined, and the world itself was caught in a crisis that lasted not for years, but for tens of thousands of years. The story surfaced in 2023, quietly, in the pages of a technical genetics paper. No exploding volcanoes, no ash beds you can dig with a shovel, just numbers. The researchers used a new tool with the oddly gentle name FitCoal, Fast Infinitesimal Time Coalescent. Under the hood, it's a more finely toothed version of the methods we just talked about. Instead of reading one long, blurry cardiogram of population size, it slices time into many tiny steps and asks at each step, how wide was the river of ancestors here? They fed it thousands of modern human genomes from around the world, African, non-African, many different populations. They asked the model to trace all those branching lineages backward through time, letting them fuse and vanish and reappear in the most likely way. And when they followed the lines not just back 100,000 years, or 200,000, but almost a million years into the past, the river did something shocking. It didn't just narrow, it nearly disappeared. According to their reconstruction, sometime around 930,000 years ago, the effective size of our ancestral population plunged. Not from tens of thousands to a few thousand, the way you might expect from an ordinary rough patch, but to around 1,280 breeding individuals. And then it stayed there. Not for a bad decade or a bad century, but for something like 117,000 years. From about 930,000 to 813,000 years ago, the main line of ancestry that would eventually lead to us seems to have passed through an eye of the needle. A long drawn-out bottleneck where, generation after generation, there were only enough effective breeders to fill a large village. If you run the numbers the way the authors did, that implies the loss of about 98, maybe 99% of the prior population. Ancestral Homo, our great-great-great-grandparents in the broadest sense, reduced to a sliver of what they'd been. Now, remember what 1,280 really means. That's an effective population size, an NE, not a head count. The real number of living bodies could easily have been several times higher. A few thousand, maybe tens of thousands scattered across a continent. Babies born and dying, groups splitting and joining, a patchwork of valleys, coastlines and refuges. But whatever the exact census, the genetic behavior of that whole ancestral network, who actually passed genes down through the bottleneck to us, looked as if only about 1,280 idealized individuals were doing the breeding. From our perspective, hundreds of thousands of years later, it's as if almost every branch of the family tree was pruned away, leaving just a few thin twigs to carry on. And these weren't Homo sapiens yet. Our species, as far as we can tell from the fossils, doesn't show up until around 300,000 to 350,000 years ago. Skulls and faces from places like Jebel Irhoud in Morocco look recognizably human. Flat faces, smaller brow ridges, though their brain cases still hold on to a more archaic shape. The bottleneck FitCoal picks up is more than 500,000 years older than that. It doesn't squeeze modern humans. It squeezes the population that would someday give rise to us, to Neanderthals, and to our shadowy cousins, the Denisovans. A stem group of ancestral Homo, standing at a crossroads of evolution, suddenly reduced to a tiny remnant. What could have done that? Here, genetics hands the story off to climate. Between about 1.25 million and 700,000 years ago, Earth's ice ages changed their rhythm. Before this point, glacial cycles were relatively short and gentle, waxing and waning every 41,000 years, paced by regular shifts in the tilt of Earth's axis. During what geologists call the mid-Pleistocene transition, that pattern broke. The ice ages stretched, deepened, became more erratic. Instead of many shallow glaciations, the planet slipped into a new mode of fewer but much more severe ice ages, on roughly 100,000-year cycles. Ice sheets grew larger. Cold snaps lasted longer. The whole system of winds, currents and rainfall that feeds life on land and sea began to lurch and stutter. For ancestral humans living in Africa and nearby regions, that likely meant repeated waves of cooling and drying, grasslands shrinking, forests contracting into green islands, lakes dropping, rivers becoming seasonal trickles or vanishing entirely. You can picture it as continents of habitat fracturing into archipelagos, patches of land where life could hang on, separated by widening deserts and hostile terrain. In such a world, big continuous populations splinter. A widespread lineage of early Homo might find itself breaking into small scattered groups, each huddled around whatever resources remained. Some would vanish when their patch failed. Others would persist stubbornly in hidden refuges, along persistent lakes, on cool uplands, in pockets where local geography defied the larger trend. If you link that picture with the Fit-Col results, a possible story emerges. The ancestors of all later humans may have been pushed into a small number of such refuges, their total effective breeding population shrinking to something like 1,280 for a very long time. Groups waxing and waning, meta-populations rising and falling, but overall numbers never climbing back to their previous heights until the worst of the climatic instability eased. From our vantage point nearly 1 million years later, the implications are staggering. Every human alive today, everyone you know, everyone you've heard of, everyone who ever lived within our species, appears to be descended from a population that, for over 100,000 years, was smaller than many modern towns. Walk through a city of 100,000 people, and then try to imagine a world where the entire future of our lineage rested in the hands of a few thousand scattered ancestors. Children playing by shrinking water holes, adults scanning the horizon for game that no longer came, elders remembering a time when the rains were more reliable and the world felt wider. Their survival, through those brutal, fluctuating millennia, is the reason you're here to listen to this story. But how confident can we be? Not everyone is convinced that the bottleneck was as sharp or as prolonged as the Fit-Col model suggests. Some geneticists point out that the method assumes a simplified kind of population, well mixed, more or less uniform through time. Real ancient humans probably lived in a much more complex pattern. Many semi-isolated groups, mixing occasionally, splitting often, maybe even interbreeding with other now extinct hominins we haven't yet found in the fossil record. That kind of structure can sometimes mimic the genetic signature of a bottleneck. Imagine dozens of small bands spread over a continent, each with their own quirks and histories. Over time, one subset of those bands might, by chance and geography, contribute more to the ancestry of living humans. Others might leave no surviving descendants at all. From the perspective of our genomes today, it could look like a sudden global crash, even if, on the ground back then, there were many more people alive in total.